So hello, everyone. Thank you very much for inviting me to Penn State to talk for close to an hour about who I am and what I do. So I'm going to be talking today about spiders on Mars, Europa, and in the laboratory, and the insights that can be gleaned regarding the processes that form them from analog laboratory experiments. So, okay. Okay. So, firstly, I'll start with a short background on who I am. Then Chris asked me to speak briefly about my career and how I got into planetary science. So I already touched on that a little bit with you, but I'll elaborate on that further. And then that will lead me into an overview of the types of analog experiments that I do relevant to Mars and Europa. So I'm an IC planetary geomorphologist, and I'm currently conducting research through a postdoctoral fellowship at NASA's Jet Propulsion Laboratory. I hail proudly from Dublin, Ireland, where I developed my transdisciplinary background with an undergrad in physics with astronomy and a PhD in planetary science. I have previous research experience at NASA Ames, the Open University, and the Natural History Museum in London. And I also really enjoy teaching, having worked for a while as a professor in planetary surfaces at Birkbeck. I also love giving talks like this and sharing my research with others. So overall, what do I do? Well, I'm interested in a multi-pronged approach to understanding icy planetary surface processes, both with and without Earth analogs on Mars and Europa. And I do this through high-resolution remote sensing image analysis and lab analog work. I think the analog work is the most fun part, though. So I hope to show you a bit about why that is the case today. Forewarning, I have lots of fun and messy videos, and I really hope they work. Okay, so... So apart from that, in my spare time, I'm also a person. And to answer your question, I like to do creative things. So I'm a big Halloween enthusiast. There's a picture of me dressed as Jupiter, and it's 80 moon babies. I believe it's recently had a few more at the costume competition at JPL for Halloween. And I also like to do my own acrylic nails. And I'm a proud cat mom to the cutest cat in the world, Pam. I have a reserved slide of many more pictures of her, which I've forced upon some people I've spoken to today already, if you want to see more. To give a brief overview of my career path to those I didn't get to meet before the talk, I first grew a fascination with planetary science back in Dublin when I was 15 years old. I remember exactly where I was at the point when I developed this fascination. I was walking by my mum in the sitting room, and she was watching the national news channel. And there was a report about Cassini detecting a plume on Enceladus, Saturn's tiny moon. And on searching images for this talk, I found this lovely one of Enceladus beside Ireland and the UK, where I'd eventually spend a lot of my time. And I thought it was quite fitting. So it's put there for scale. Yeah, so anyway, the news report of a plume captured my attention, especially since it might signify a subsurface water ocean. And I immediately wanted to learn more about space. In Ireland, certainly at the time, there were very few resources to learn about space. So I spent a lot of time on the NASA website learning more. And I was particularly captivated by icy planetary surface processes. At the time in high school, I decided to take physics, chemistry, and try to do better at math. And I dreamed of studying space somehow. I have my mum to thank for encouraging my interest, despite there being few people to talk to at home at the time. She managed to find an Irish engineer who worked at Kennedy Space Center and somehow timed that with a surprise trip to Florida, which I'm very grateful for. And we got a tour of Kennedy Space Center given by this engineer. And that really, really sparked my interest further. Admittedly, I then went on to have a fairly non-linear journey towards what I really wanted to do. And I'll be totally honest about my path in the hope that it might help somebody else in navigating their career. So I did my undergrad in physics with astronomy at UCD. And during this time, I got the opportunity to do a study abroad program at San Jose State in California, where I had a really inspiring professor who really cemented for me that it was icy planetary surfaces I was interested in. So naturally, I started a PhD in stellar astrophysics. So I joke, it really wasn't for me. And I was pursuing something secondary to what I really wanted to do because there were no options at home. And I probably should have just taken a bit of time to decide what I wanted to do. But in the end, I was very lucky. Fortunately, right around the end of that year, the wonderful Mary Burke returned to Ireland from the US, and she was a planetary geomorphologist who had a project on icy surface processes available. And so I got to be around friends and family while making this change. Mary's a geomorphologist who took a chance on a physicist, and there were a lot of language barriers to begin with. I had a steep learning curve, but ultimately I think that the transdisciplinary collaboration made my project a successful one. I was PI on an Irish Research Council 3-year fellowship, and also on a Europlanet proposal to get time to do CO2 ice sublimation work in a Mars simulation chamber, which I'll tell you about later. And we published some interesting papers, won some awards, and most importantly, I got to connect with the Mars polar community here in the US at international conferences, some of whom I now work closely with today. And then after the PhD, I moved to the UK and I applied for fellowships and postdocs to continue the next stage of these experiments. But as I said earlier, the funding landscape in the UK is unfortunately not great. I was lucky to get a couple of short-term postdocs on different topics, like identifying the potential source locations of the Sherga-type Martian meteorites at the Natural History Museum in London. And this definitely broadened my remote sensing skills. And I met some friends for life. But then the pandemic hit and I was talking to those friends for life through a camera for about 1.5 years. And unfortunately, when that 1 year of funding ran up, I was applying for jobs when everybody else was. And I spent about 6 months unemployed at home in Ireland with my parents. So if you'd have told me then where life would take me in the next year, I absolutely wouldn't have believed you. So eventually I got a part-time teaching position in geology of the solar system at Birkbeck University of London. And I moved back to the UK, and I was eventually made permanent there, which at the time was truly beyond my dreams because I really loved teaching and such jobs were so scarce in the UK. However, these long desired experiments were still in the back of my mind. So I was absolutely shocked after almost 3 years of applying to do them to various fellowships that NASA funded our proposal. The project will be carried out at JPL and led by the American PI. And as many of the professors here will know, you can't take NASA funds out of the US. So it was a choice between, after all that instability, to pursue this stable job where I enjoyed the teaching and give away the research I really wanted to do, or to take a chance and come to the US and pursue that research. Although I'd absolutely love to be a professor again in the future, I had to pursue that research that I really loved, and I took the opportunity. I'm now here in the US at JPL, and I'm thoroughly enjoying doing the research. So anyway, thank you for listening to my little life story. I'm happy to answer questions on that at the end of this talk, but for now, let's move on to the science and telling you about my research. I hope to convey to you why all this was worth it. I've decided to talk about my research chronologically, since that fits well with also discussing my career path. So until recently, Mars polar science has been my bread and butter. I focus on present day Mars, which is shown in this movie here. The stuff you can see changing and growing literally today, which in its own right is fascinating to me, that we can see surface change on Mars year in, year out. And while the planet Mars has undergone drastic shifts in climate regimes, you may have learned about that on your courses here at Penn State. Today it's cold and dry with an average atmospheric pressure between 6 and 10 millibars. Daily temperature ranges near the equator are from 293 to 233 Kelvin, and the planet's atmosphere consists mainly of carbon dioxide, which you can see here on the surface depositing on the surface of sand dunes. So like Earth, Mars has polar ice caps, seen in the images below here. And importantly, because the planet has an axial tilt of about 25 degrees, it experiences seasons. So while both hemispheres have perennial caps composed mainly of water ice, a seasonal CO2 cap, which you're seeing here in this movie, descends on the surface in winter and in spring, and this sublimates or changes directly from solid to gas. Signatures are left on the surface by this seasonal cycle, like you're seeing here with these dark fans and blotches. And those are what I'm most interested in studying, the features that change year in, year out on Mars. So There are many surface features on Mars that do have Earth analogs, and for example, putative glacial and periglacial surface features, gullies, and so on. And in understanding their formation, we benefit from decades of in situ measurements of similar features here on Earth, which are often formed by water in the liquid or ice phase. But what about when we come across features that we're totally unfamiliar with here on Earth, such as these linear gullies here and these spiders? Generally, such features are active today on Mars, and they grow and extend in some way in a climate that doesn't support ongoing liquid water action. And many are timed with the spring sublimation of the seasonal CO2 ice cap. Two particular features of intrigue to me, as I mentioned, have been these features, linear gullies and spiders, which I'll elaborate on further. And both features have been observed, and change has been detected for them with the high-res camera on board the Mars Reconnaissance Orbiter. And this is a camera that's capable of resolving features as small as your kitchen table, and therefore detecting seasonal change. So, I don't want to start that movie. Sorry. Well, it's started now. Okay. Well, you can watch it while I'm talking. So I'll touch on linear gullies briefly now and come back to my main love, spiders, in a moment. So linear gullies, as you can see in the left-hand image here in Russell Crater on Mars, you're probably being really distracted by that movie now. They are long, often sinuous channels found on sand dunes on Mars. And unlike gullies on Earth, they terminate in pits rather than debris aprons. So in 2013, my current postdoc supervisor, Dr. Serena Denega, my PhD supervisor, Dr. Mary Burke, and one of my biggest idols in planetary science, Dr. Candy Hansen, went out in the field. And as you can see in this movie here, they originally hypothesized that the gullies were forming by sliding CO2 ice blocks that broke off over steepened cornices in spring and slid down dune slopes. Okay, now you're seeing Serena talking, and I had not meant for the whole video to play. So I'm going to go back. Yeah, so they went out in the field, and they basically bought CO2 ice blocks in the store in Utah and slid them down the dune slope in order to investigate whether similar morphologies to those on Mars would form. And they did find that the blocks slid down the slope, assisted by a lubricative gas layer, and they kept on going and carved channels. So what's happening here is something called the Leidenfrost effect. And this is a phenomenon where a substance comes in contact with a surface that's much hotter than its sublimation or boiling point, and it will levitate on a cushion of gas. So that's what's happening here. And that's what we think is happening on Mars. So they verified that the blocks kept on going and formed channels. However, there was still work to be done on how the pits at the end of the linear gullies would form. Okay. There were experiments to do investigating whether blocks would form in situ. So whether blocks would form pits in situ under very low pressure and temperature Mars-like conditions. And at the time, I didn't have access to the beloved cryovacuum chambers that I work with now. So I at least tried to eradicate the humidity that we experience on Earth by building a low humidity chamber, seen in this diagram here, which I evacuated of air or of water vapor by flowing in CO2. I then placed CO2 blocks of various volumes on a granular bed in that chamber, and investigated the morphologies that were produced when an in situ sublimating CO2 block came in contact with granular substrate of various grain sizes. So we found that for coarser grains, that the blocks produce morphology very similar to those we see for main pits on Mars. So the main pits are what you see around here with the white arrows here. They're the main pits at the terminus of the gully channels. So the blocks just dug into the sand and produce features similar morphology surrounded by levees to the pits on Mars. And then for the finer grains, the blocks burrowed, and they produced these endogenic collapsed pits here in the, for the people online, the lower right-hand corner image here, these were formed by subsurface jets, which emanated from where the block burrowed downwards. And then we also found another type of pit morphology, which we think formed by granular clustering in the gas jets, wherein the clusters then impacted the surface to form these little very, very tiny pits upon returning to the surface. And we think they may have relevance for these little detached pits surrounding the main channels. We calculated the volumes eroded per given block dimensions, and then we surveyed several sites on Mars, which you can see in these images here. We measured the pits on Mars, and we also measured the sizes of high albedo objects in some of the pits, like this green arrow one here, which we think may be blocks of CO2. And so we reconciled the given volume eroded per block size and reconciled that with the measurements we made on Mars and we found that they agreed with each other. So that suggests that these pits were formed by CO2 sublimation as proposed. And a surprising outcome of this work was discovering for the blocks that didn't burrow, that I mentioned earlier on, that we saw these little channels forming underneath them where the gas escaped at the sides of the block. And some were sinuous, some were dendritic. And this was kind of the twist or turn that would begin many a year-long obsession with a very one particular pattern in nature. And for the rest of this talk, that's what I'll focus on. Spiders. This brings me to spiders, more formally known as araniforms. For immediate sensation reasons I don't need to go into. Spiders are dendritic or branched negative topography networks of troughs found among the Martian south polar layer deposits and surrounds. And they have a whole range of morphologies, which we can see in the top left panel images here, ranging from starburst to linear to half, and many others, ranging from less than 50 meters to greater than 1 kilometer in scale. And each spring, we see relatively dark fans and spots emanating from their centers and troughs, like seen in this GIF here. But other than that, for the large radial spiders surrounding the SPLD, we've seen no change in their growth. So we see the fans and spots emanating from them, but we haven't detected any growth in the spiders in the present day. However, a recent detection of newly growing sand furrows and dendritic troughs, seen in the lower left-hand image here, which are found within dune fields, this raised the question of a link between morphology, activity, and environmental conditions, past and present. So over the years, folks have mapped the spiders sparsely with the MOC camera on board Mars Global Surveyor, and later the CTX and HiRISE camera on board the Mars Reconnaissance Orbiter. And lately at JPL, we've been working on building a contiguous map seen here in the upper right-hand corner with the CTX Murray Lab Global Mosaic. So some interns have been doing some great work with us on that, and this is ongoing work. And we've been trying to build a transect of their individual submorphologies, which you might see here, trying to look at whether their morphologies vary with latitude and inferred ice thickness. To try and understand their environmental controls, such as grain size, ice thickness, groundwater ice presence, etc. And these drive their morphologies and relative activity levels. However, to really understand this relationship, we really require empirical data. So I have a little movie here of how spiders form. Regardless of morphology and activity level, all of the features I mentioned there are proposed to form by some variant of the Kiefer model seen in this movie here. So the model proposes that in winter, translucent slab ice condenses on the surface of Mars, and in spring, sunlight penetrates the ice, heating the regolith beneath it and building up pressure beneath the ice. Eventually, the ice will rupture and gas will rush towards, so this keeps going. The process occurs year to year. So the gas will rush towards the vent and scour the surface in its wake and deposit the material that is entrained in the form of a plume on top of the ice. And then the plume falls back on the ice, and what you're seeing in that GIF previously is the remnants of this activity on top of translucent ice So you see the spiders beneath the ice, and then you see the fans and spots on top of the ice. So what's left is a network of dendritic troughs, which makes up a spider. And as I said, this is proposed to repeat year to year, growing the spider at a rate that really hasn't been fully quantified. So this was a study that we did during my PhD that got quite a lot of media articles that almost all opened with the link between me and David Bowie's band. So I ran experiments to test the Kiefer model and made the first empirical connection between high velocity sublimating CO2 gas and spider pattern formation under Mars pressure at the Open University Mars Simulation Chamber, which is this chamber here. So for these experiments, I drilled holes in the center of CO2 ice blocks and I suspended them from a claw as I lowered the pressure in a planetary simulation chamber. And I eventually placed them in contact with a bed of granular substrate. So I capitalized on the Leidenfrost effect, which I told you about earlier. So I knew that when the blocks came in contact with the substrate that they would sublimate. And what we really wanted to see was what type of patterns would form when sublimating pressurized CO2 gas came in contact with granular substrate and escaped through a vent. So in each case, a plume was generated, which excavated material from beneath the block to form spider patterns, which we saw when we lifted the block up. So here's some examples of the spider patterns that we saw. And by building digital elevation models of the surface, we could measure the depth and the surface area covered by the spiders. And we found that they were more dendritic and covered more area for finer grains and smaller vents. However, these experiments were performed at room temperature, which is not consistent with Mars polar springtime conditions. And also we drilled holes in the center of CO2 ice blocks and placed them in contact with granular substrate. So this wasn't really the conformal translucent slab ice layer situation or the type of gradual heating induced by incident solar radiation that we would expect on Mars. So I just want to show you this fun movie as an aside. Yeah, so while we got a neat paper out of that work, the real highlight of these types of experiments are the very fun movies and the understanding that phase changes behave very differently under different planetary regimes. So this happened when we dropped a CO2 ice block in the chamber. And as you can see, I really didn't expect it to be this violent. So I'm running around the chamber trying to chase it and get a movie. And I was not allowed to do this again because it can wreck the pump. So this is my movie of it. But this is what some colleagues have dubbed the laundry machine. But it really shows the efficacy of CO2 sublimation under Mars pressure conditions. And also the bed reached a temperature of about -10 degrees Celsius, so like 260 Kelvin eventually, and the block was still going. So even with a very different, small difference in temperature between the CO2 ice block and the substrate, there was a lot of geomorphic efficacy going on, and material was being thrown all over the chamber. So you can imagine those blocks on the sand dunes sliding down, excavating material beneath them. So yeah. So from those lab experiments, we hypothesized that for spiders on Mars that form contemporaneously, so where cracks in the seasonal ice were forming the spiders around the same time, we might observe that spiders with greater distances between them and smaller inferred vent sizes would be more dendritic because those spiders would be formed by higher velocity gas. So to test this, we surveyed 3 sites on Mars, which had clusters of spiders with similar morphologies. So a lot of these spiders tend to cluster together, as you can see here in these movies. Some of them intersperse, but they tend to appear in fields, or as one of my students called it, swarms of the same type of spider. So we surveyed clusters of spiders, and we measured the distances between them and the sizes of their full extent, and we used the size of their central pits as proxies for their original vent sizes. And we found that these groups followed the trend predicted from lab experiments. So the trend of the further spaced the vents are, the more dendritic the spiders will be, and the smaller the vent size, the more dendritic the spiders will be, because there's higher velocity gas operating to erode them. However, ongoing mapping efforts, which we're doing in collaboration with the great summer interns that we've been having, are going to investigate these trends further, as well as aim to place better constraints on the ages of spider clusters using relative stratigraphy or the analysis of local geologic features in order to understand their ages. So along the way, we've found and named some new spiders. So that's the fun part of this work. So you can give the features and sites informal names. I named one Dublin, which is a bit cheesy, but however, these are sunflower spiders, called these flowing spiders, and these ones segmented and these ones spiky. So you can kind of call them whatever you like, but these were definitely new morphologies that we hadn't seen before. So we're going to take a little bit of detour now to Europa for a moment, if that's okay. So prior to this year, I was really placing an emphasis on how spiders were like nothing seen on Earth or elsewhere in anything I was writing about them. And a few months into my postdoc at JPL, I was really amazed when I discovered the spider on Europa. So Europa is Jupiter's icy moon, which we'll be headed towards with the Europa Clipper flagship mission in 2024. And I'm lucky to get to visit Europa Clipper whenever I want to. Well, whenever a US colleague lets me into the room. And I really wanted to get in the Clipper team when I arrived at JPL. So when I got to JPL, I got in touch with Bob Populardo, who's the project scientist of Clipper. And I asked him, you know, how do I get involved? And he said, you know, if you do a project relevant to Europa, you can become an affiliate. So that was my goal of last year. So I was talking to my colleague Marshall, who was on Clipper, and he's a Europa expert. And he said to me, have you ever seen the spider on Europa? And you know, granted, this is a pretty genetic term for this feature, I think. You know, they've named it a spider after the spiders on Mars. It's not very well resolved. We can't see any dendritic arms, but I think someone else called it an asterisk, which I think is a bit more apt. But it does certainly look like how some of the spiders appear on Mars when they're not very well resolved. So it could be dendritic, we don't know. And it's also in an environment that's not very much like where the spiders form on Mars. It's not mobile, dusty regolith. It's an icy surface. But anyway, I took the fact that it's in Manannán crater, named after the Irish mythology, son of the sea in this image here, to be a sign that I should research it further. In my research, I found that a team of researchers had hypothesized that it formed from plume activity from an impact-induced subsurface brine reservoir. So the researchers suggested that it consists of a network of fractures and formed in a similar way to the spiders on Mars. However, as we went through there, spiders on Mars are not fractures. Also, despite keen efforts, the jury is still out on, as to whether there are plumes on Europa. So I wondered if it might be something else, and I researched things like dendritic patterns in ice. So you can imagine my amazement when I discovered lake stars. Have any of you seen these? No, I know, I'm always amazed. I don't know how I've never seen them. I've been researching this pattern on Mars for so many years. They're absolutely beautiful. They're prevalent on frozen ponds and lakes right here on Earth. So these remarkable features look exactly like Martian spiders in pattern, rendering the opening statement of spiders are unlike anything seen on Earth pretty moot. So granted, there's certainly an example of the issue of equifinality, where similar morphologies can be arrived at from very different formation processes. And they're definitely formed by a totally different mechanism to spiders. But they form when snow falls on a lake that's covered by a layer of thin ice. And the weight of the snow forms holes in the ice, and eventually relatively warm water will flow through the holes and spread out through the porous snow, melting smaller grains at a rate faster than the coarser grains. And this causes an instability in the flow. And the flow, basically the flow wants to spread out evenly, and that dendritic pattern is energetically favorable. So the dendritic pattern follows the path of the flow, the melting in the flow. And eventually the lake ice freezes again, encasing that pattern within the ice. I wondered if something like this could happen on Europa, albeit under very different pressure and temperature conditions. So I'll just show a little movie of these features while I continue on with my story. Hopefully, yeah, there's some text on it, but I really like this movie because it shows some stunning examples of them on Butterfly Lake in China. And those lake stars are about 100 meters in size. So I think they vary in size based on the size of the lake and the thickness of the ice and so on. So you can see them compared to the size of the bridge. I think they're really beautiful. So I posed this idea to my colleague, Jennifer Scully, who was working on mapping Manannán at the time. And this evolved into a collaboration where she has done some morphological analysis in the Manannán region, which indicates that the radiating arms of the spider don't appear to display any structural features and so may not be fractures. And together with a cross-disciplinary team of planetary scientists and engineers, we developed a new hypothesis for the formation of Manannán spider based on the formation of lake stars on Earth. So moving on, I have another little animation to show my proposed hypothesis. So we suggest that the feature may originate from a process similar to that forming lake stars on Earth, where its arms are not fractures and instead are low albedo ice surrounded by frozen impact slurry. So I'll just play this movie here now, which shows a slice of Europa. So we have Europa's ice shell. Yeah, so we get an impactor coming in, and following impact, a transient localized atmosphere developed above the impact site, and a brine pool formed locally beneath the surface. And yeah, so I'll wait for the brine pool to form. Talk you through it. So during cooling, impact slurry covered an ice layer above the brine pool, and eventually the ice cracked, allowing liquid water to flow to the surface and rush through the slurry, spreading out in a similar pattern to the lake stars on Earth. And as temperatures and pressures were elevated at this time, and also by the presence of salts, water could remain as in a liquid state transiently. And also partial vaporization upon surfacing of the water would elevate the localized pressures too. So we propose that the spider has a low relative albedo because of its higher salt concentration, which presumably darkened over time due to radiation exposure. And you might have seen something on that when Kevin Hahn gave a talk about the darkening of the salts. That's what we're proposing for this. Okay, so I did some lake star field tests in Breckenridge, Colorado. I was actually on vacation, saying that I wouldn't do any work on vacation. And then after studying these for a year, they popped up on the lake and I was very excited. So I performed field tests to explore the parameter space surrounding their formation, because actually not a lot of work has been done on these features and very few people seem to know about them. I actually got in touch with the most recent person who modeled their formation that I could find, and he's now collaborating with me on this work. So that's been really great that he is actually alive and willing to talk to me. So I went out and I used a turkey thermometer to measure the temperature of the ice and the snow and the water. And then I used the measure tool on my iPhone to measure them. So these were pretty small lake stars. They were about 2 meters to 20 centimeters in diameter. There were some very small ponds in the region, and the ice was about less than 5 centimeters thick. Interestingly, the average ratio of their full extent to their central depression seemed to follow a similar trend to the spiders on Mars. They seem to have similar spacing. I need to investigate that further. I don't know. I think there's room for some modeling there that I'd be interested in pursuing. But the average temperature of the lake water was 0.8 degrees Celsius, and the average temperature of the ice was just below 0. And their patterns are not negative topography, but they're frozen clearer ice within more opaque ice, as you can see here. I had my husband go into the lake and hack off pieces of ice so that I could investigate them further. So many lake stars were observed in layers. If you can see here, there's some low albedo kind of spots, and those are lake stars, and they're covered by layers of ice on top of them. So a lot of hypotheses for features on this just reminded me of some hypotheses for features on Europa that are formed by surface brine effusion, they're generally covered in a crust. So that could be something that might be going on for their formation on Europa as well. And these Darcy flow lines surrounded many lake stars, which are indicative of the type of flow that forms them through a porous material driven by a thermal gradient. However, we still needed, this was just me out in the field, exploring the conditions under which they form on Earth. We still need to know if patterns like this could actually form under European conditions. I've been doing some lab experiments in order to test whether the parameter space surrounding lake star formation explored in the field tests extends beyond Earth conditions. So I performed experiments where liquid water was flowed through Europa granular ice simulant. So if you can see it here, the granular ice simulant was developed by the Europa Lander robotics testing team. And they kindly gave me their granular simulant when they were done with it to do these experiments. So as a first step, these experiments were performed under earth pressure in this liquid nitrogen cooled glove box. So it goes down to about -40 Celsius. And it works by duty cycling liquid nitrogen spray into the chamber to keep it cold. So I put this fine spray granular ice simulant on a tray, and I explored a few temperature regimes. So the first was 0 degrees ambient temperature and a 0 degrees Celsius container and granular ice layer and room temperature water. And then I did the same container and ambient temperature conditions and -4 degrees Celsius water, and then 0.5 degrees Celsius water. And then for an extreme, I looked at an -30 degrees Celsius ambient temperature. And then we flash froze the simulant in liquid nitrogen, and it was about -100 degrees Celsius. And then we used room temperature water. And these experiments were also repeated for salty simulant, which had magnesium sulfate salts dissolved in it. So just a little movie of what we were doing. So for each trial, as I said, I cooled the container using the liquid nitrogen glove box and spread the granular ice on top, flowed water through it. I used a wash bottle of outlet diameter 1 millimeter, and I placed it very near the surface, and I flowed water through the center of the granular ice at a constant rate until a lake star pattern appeared or did not, and the water reached the edge of the simulant. And I recorded the volume of the water used in each case. So if I can, yeah, it just shows what I was doing. So hopefully you can see the patterns start to develop there. So I made little mini lake stars in the lab. Yeah. So there's some images of some of them that formed. In each case, features quite similar to lake stars, though obviously much smaller in scale, formed. And arms developed in all cases, but they were less distinct for the salty simulant. And for the ambient room temperature case, the dendritic arms were more apparent. And interestingly, this pattern even formed when I flash froze the simulant, and it was at about -100 degrees Celsius. But it did freeze very quickly. But it was pretty exciting that it still formed under those conditions. And this is ongoing work, but we're almost finished writing up a first paper on it to present the hypothesis. There's some modeling work in there as well, but that's not finished, so I decided to leave that out. So hopefully you might see that soon. And so, yeah, back to Mars. So I'd like to go back to Mars and finish this talk on what I deem to be quite I personally think it's a high point in my career. So as I alluded to at the beginning, I had a few years of trying to get funding to do the work I'm doing right now. And you'll recall that my previous spider experiments, while they showed that sublimating CO2 gas could generate spider patterns, they didn't model the Kiefer model in a realistic sense. And we needed a conformal condensed CO2 slab ice layer, and also the realistic temperature regimes that we expect for this process on Mars. The extraterrestrial So the Extraterrestrial Materials Simulation Lab, EMSIL for short, Cryovac chamber, which you can see here, is the chamber that I work on. It's a state-of-the-art facility which is capable of simulating Martian and other planetary atmospheric conditions. It's 45 centimeter in diameter and 60 centimeters long, and it's capable of temperatures down to minus 200 degrees Celsius and pressures to 10 to the minus 5 torr. And the interior walls of the chamber, the back and cylindrical shroud, consist of liquid nitrogen shrouds. So liquid nitrogen flows through them to cool them. And the interior of the chamber contains a 25 centimeter by 45 centimeter liquid nitrogen cooled aluminum plate. And liquid nitrogen tanks can supply cooling power to the chamber. So you can see them here, and they flow in through the plate and the shroud to cool it down. And the shrouds and plate can be controlled by a proportional integral derivative controller, which is regulated at any temperature in the range of about minus 200 degrees Celsius to room temperature. And the chamber is also equipped with a Pfeiffer vacuum ACP15 turbo pump. And this pumps down to Mars pressure in about 5 minutes, unless we get some impurities in the chamber, and then it takes its time. So our current experiments set out to firstly investigate whether plumes and spider patterns can be generated when a conformal condensed layer of CO2 ice is insulated, and validating the Kiefer model on the small scale. And secondly, to explore the parameter space surrounding different spider morphologies in order to generate hypotheses regarding local conditions, past and present, at the Martian South Pole, where they formed when reconciled with mapping work. So we're using this chamber, which, as I explained, is capable of simulating Mars polar temperature and pressure conditions. When we reach the conditions that we need, we can then flow in CO2 once these conditions are reached, which then condenses as ice. So we're targeting the regimes identified by Porciankina et al. So Anya Porciankina has done some fantastic experiments to identify where translucent CO2 ice will form. So on this plot here, we're hanging out at about here. So this is about 4 to 10 millibar in pressure, and 130 to 155 Kelvin. So we're hanging out at those pressures and temperatures, and we're flowing in CO2 and condensing it as translucent slab ice. So firstly, as you can see here, we grew the translucent slab ice onto the plate. Now it's cracked because, you know, the sky is a little bit warmer than the ice, so it cracks and then it anneals, so it heals quickly, but it is translucent. And we got it to be about 3 centimeters thick, which is the thickest anyone has gotten to my knowledge. And this is due to the dimensions and the cooling capabilities of the chamber. So this is our process for the experiments. We then moved on to growing the CO2 ice on glass spheres and MMS dust. And to do this effectively with a thick layer of granular material, we need the material to be cooled throughout. So shout out to our engineer colleagues who suggested this little cryopod, which is essentially a lunchbox sized pod, liquid nitrogen bath, where you can place a tray of your sample in a liquid nitrogen bath and cool it down. So what we do is we pour the sample in the cryopod tray, and we arrange a strip heater below the surface and thermocouples near the surface. We then insert it in the cryopod and we fill it with liquid nitrogen, and we wait till the surface of the sample reaches minus 190 Celsius. And so while we're waiting, we then pump the chamber down and we cool the plate and the shroud. We then backfill the chamber with nitrogen gas, and we quickly insert the tray on a liquid nitrogen cooled plate, which has been mostly insulated apart from where we're going to put the tray. And we pump down at 1 millibar per second so that we don't blow away the sample. That's an issue we ran into. And then we stop at about 2 millibars. And at this point, the surface is about minus 150 Celsius. And we use a sponge to diffuse the CO2 coming in so that it doesn't blow away the dust. And we try and hang out at the discrete ranges that I mentioned to you before. And then we build up an ice layer, and we eventually activate the heater to crack it. eventually we're going to move on to then using a solar simulator in order to fully simulate the process I described to you above. So I have to say, this really hasn't been easy. We don't have a technician, so I've had to train up in that domain. And the chamber has been really good at challenging me and training me. So there's been various leaks, things breaking, whistling, you name it. And this is, this has been going on for weeks now since the end of last year. And it's almost broken my heart until late of a Friday evening, a couple of weeks ago. I was very excited and happy. So I'm going to show you a little movie now. Okay, the movie's playing. Hang on. Let me go back. Okay, so hopefully that movie's playing. Let me go back. Plays on. So what you're seeing there is the sponge on top. And I thought I was seeing a little spider down here in the lower left-hand corner of the sponge. Can you see a little bit of a shadow there? I thought I was going a little bit mad because I was really hoping to see this. And then I saw the jet coming out from it. So I started screaming naturally. I was very excited. And my lab manager came running in thinking I was having a medical emergency. And yeah, we were super excited about this because we've been trying to do this for a very long time. And what you're seeing there is translucent CO2 ice on top of the simulant. And the interface between the ice and the MMS dust is heating up and it's cracking and you're getting jets coming out from the subsurface. And then what's happening at the center is where the heater is, we think there's slumping happening. We think that there may be CO2 diffused into the regolith, which actually has a lot of implications for models of seasonal processes on Mars. So we're going to look into that further, and that the heater is just sinking. So yeah, I'm going to show you a more fun movie now of what is absolutely no doubt a plume. So that was pretty fun to see. So that's after I activated the heater and the ice cracked and you're seeing dust being thrown out very violently. Okay. So I'll show you the aftermath. As you can see, the plume reached the top of the chamber. There's a lot of cleaning involved in this work. And at the back of the top image from the first trial that I showed you, hopefully you can see a little channel where I think a plume at the back was operating. And at the foreground of the bottom image, you can see a little pit where that first plume was operating. And I think that the dust currently is too fine to preserve any morphologies that are formed beneath the ice layer. So I'm excited to try this with coarser grain sizes. One main question we have in this work is, did the CO2 diffuse into the regolith and how far? And is sublimation from within the regolith another way by which different spider morphologies might form? And hence are some morphologies indicative of near surface ground ice on Mars? And how might this tie into deposition modes and substrate properties on Mars? How are we doing for time? Sorry. It's been Pardon?
It's 4:50.
Okay. This ends at 5:15?
We got questions at some point.
Okay, cool. So I'll finish up now. Okay, cool. Thanks. So yeah, as I said, this work is ongoing. There's a movie there showing a side profile of the plume. And we've only just nailed down the methodology after a long time of other groups, as well as ourselves trying to get a plume. So the next steps will be to really refine this methodology to increase the ice thickness and control the plume and grain size so that topography is preserved. We also want to get a more even distribution of the translucent CO2 ice on the surface, as we think that we're getting a mix of translucent and triangular crystal CO2 due to uneven cooling. We're also going to cool the CO2 prior to flowing it in order to build a more thicker layer. And of course, we're going to then move on to using a solar simulator instead of heaters and implement a microscope to characterize the ice type. And in the meantime, we're going to pray that the dust doesn't destroy our pump. So if you'd like to read more on Martian spiders, the work is here. We have a review paper coming out in the next week or two, which will probably be a good place to start on learning about spiders. So yeah, And then just some closing remarks and take-home messages. Icy planetary surfaces behave in weird and wonderful ways, and analog lab experiments are essential to understand how the physics behaves under these regimes. And to the students, it's okay to have a non-traditional route, whatever that is nowadays. Just take the time to carefully think about your future and to lean on your support systems. And on that note, role models are really key to attracting and most importantly, retaining people in planetary science. My journey has been supported by some incredible role models like my mom here, who I was lucky to show JPL recently, my PhD supervisor, Mary Burke, my postdoc supervisor, Serena Denega, and my ultimate role model in planetary science, Candy Hansen, who I later found out after all of my journey was the person who led that Enceladus plume study. And now I work with her, and it was really wonderful to show her that video of the plume on Mars, because she's been hunting for those on Mars for a very long time. So I would say reach out to these people, chat to people. Don't be afraid to chat to them. They've been in your shoes before. And don't limit yourself to one planet. That's something Candy told me. She said, find a niche process and question how your understanding of that process may be applied to other planets or disciplines. And this can be closer to home than you think, certainly in my case with the lake stars. And yeah, if anyone has any hypotheses or anything they'd like to test in our chamber, feel free to get in touch.